Good morning everyone. Today we are going to see design of machine elements in that unit 4 springs and engine components. So I am SK Karthikeyan, Associate Professor, Kongunadu College of Engineering and Technology. Today we are going to see unit 4 springs and engine components. As you know, springs is an element which has a action that when you applied a load on it, it going to change its shape and regain its shape after releasing the load. So mostly they used in the automobiles, railway wagons, valves, watches. The functions are it provide cushioning effect and absorb shock and impact load, and it is used in the spring balance as a measuring device, and it can store energy like in clock and toys, and it's mostly used in brakes, clutches, and also machine elements like cam and followers. Coming to the types of spring, the major classification is start from helical spring. It has two variety like closed coil spring and open coil spring. The next one is spiral spring, then leaf spring, then disc or belly spring, then conical spring. And coming to the end conditions of the spring, you can see four diagrams which has a specific end like a structure. The first one is plain end, and it has a poor seating arrangement. And next one is plain and ground end. It has a better seating space than plain, that is better than a plain type. And third one is squared end, and fourth one is squared and ground ends. So mostly they are used in the high stress applications. And coming to the problem, and you see it's a gas engine. They have given some data like mean diameter of the spring 37.5, and the maximum load on the spring is 450 newton, and deflection of the spring is 12.5, and the working stress is 300 newton per millimeter square, and rigidity modulus, that is G, is 0.8 into 10 power 5 newton per millimeter square. So we have to find the size of the wire and number of coils. So in the page number 7.100 in the PSG data book, you have the formula for shear stress, that is working stress, as tau equal to Ks into 8 PD by pi d cube. Substitute all the given like the diameters, the load, and the shear stress. You can get the wire diameter as 5.2. So we're going to choose the nearest value, that is from the table. So it's going to be 5.3 mm. Then coming to the next calculation, number of coils, we have one more formula that is available in the page number 7.100 in the PSG data book, that is y equal to 8 PD cube n divided by g d power 4. Substitute all the values. So n is the only unknown we have to find. Keep it in the left side and remaining in the right side. So you got 4.156. Make it as a round value because it's going to be a count. So n is a 5 is the final answer. And coming to the end condition of a spring coil, we here consider that squared and ground end. So from the table in the page 7.101 in PSG data book, the total number of coil, that is nt equal to n plus 2. This is the formula taken from the page number 7.101. So substitute n value here, that going to be 5 plus 2. So you finally attain total number of coils is 7. And coming to the second problem, they have given diameter of the wire D equal to 1.25 and the yield strength as 750 newton per millimeter squared, and mean coil diameter as 12.5 mm, and number of active coils is 14, and modulus of rigidity as 0.85. So 85 into 10 power 5 newton per millimeter square. Here they are asking stiffness of the spring and solid length, that is the LS of the spring. So from the page number 7.100 in PSG data book, we have the formula C equal to D by D. It's a spring index formula. So substitute this, you're going to have C as 10. Then coming to the next formula, stiffness, that is available in page number 7.100 in PSG data book, that is Q equal to GD8C cube N. So substitute all the values and you finally got 0.948 Newton per millimeter. It's going to be around value, we make it as 1 Newton per millimeter. Then the second one is solid length. we have to find the LS value that is available in the page number 7.101 PhD data book. So we consider it's squared and ground. So the total number of coils nt equal to n plus 2. So already we have the value of n. So substitute in that, you're going to have 16 as nt value. Then coming to the LS formula in the same page, it is d small d into n plus 2d. So substitute all the value, you're going to be 20 mm. So finally we attain two answers. Then the third problem, here they have given outside diameter of the spring as 80 mm and wire diameter as 12 mm and maximum axial load on the spring, that is P equal to 1 kilonewton, and the number of spring coil as N equal to 10.5 and modulus of rigidity G equal to 0.89 into 10 power 2 kilonewton per millimeter square, that is converted into Newton by adding it 10 power 3, that is 0.89 into 10 power 5 Newton per millimeter square. So the questions are maximum shear stress, total deflection and factor of safety. So we know there is a formula, that is mean diameter is outside diameter plus inside diameter divided by 2, that clearly stated in the given picture, you can see, and from that we can find the mean diameter by substituting the unknown values. So for that we have to find di first. So di equal to d naught minus 2d. So we know the value of d naught 80 and small d as 12. Substitute and find the value of di as 56. Then once again substitute the same in the mean diameter formula. You can get the mean diameter d as 68 mm. So from this we can find the spring index using the formula d by d, which is available in the page number 7.100 PhD data book. Then we can find the Ks value, that is wall stress factor. That formula is available in page number 7.100. So that is going to be Ks equal to 1.25. Then we as usual we going to use the shear stress formula, that is Ks tau equal to Ks into 8 Pc divided by pi d squared. That is also available in the PhD data book page number 7.100. So we can find the value as 125.11 Newton per millimeter squared. Then coming to the total deflection, for getting the value of y, we go for using the formula which is available in page number 7.100 in PhD data book, that is y equal to 8 Pc cube n divided by gd. So substitute, you got 14.26. Then coming to the last question, factor of safety, we know factor of safety as yield stress divided by working stress. So we are going to assume some value like that is yield strength. So we consider it going to be a C50 steel, and for that the yield strength is sigma y equal to 340 Newton per millimeter square. That is available in the page number 1.12 in the PhD data book. So substitute in that, the only unknown is n, that is factor of safety. You got it as 2.72. Make it as a round value 3. So that's all. And coming to the problem number 4, they have given diameter of the spring as spring wire as 8 mm, that is small d, and outside diameter of the spring is 75 mm, and number of active turns are 6, and permissible shear stress is 350 Newton per millimeter square, and modulus of rigidity G equal to 84 kilonewton per millimeter square. So the questions are axial load on the spring and deflection of the spring produced, that is Y. So as usual, use the D formula, D naught plus dI by 2, and also use the formula of dA equal to D naught minus 2D, as like from the same previous problem. So find the D value as 67 and find the spring index D by D using the formula D by D, and it's going to be 8.375. And coming to the wall stress factor, this formula is available in the page number 7.100 in PhD data book. So use that. So we got it as Ks as 1.175. Then coming to the another one, shear stress, permissible shear stress formula, that is available in page number 7.100. Substitute the unknowns and you can get the unknown as, that is P as 893.9 Newton. Then coming to the final question, deflection, this formula available in page number 7.100 in PhD data book, that is y equal to 8 Pc cube n divided by gd. So substitute all the unknowns and you can get it as y equal to 37.5 mm. And coming to the fifth problem, a compression helical spring is required to exert a minimum force of 250 Newton and maximum force of 600 Newton. So they have two p values, maximum and minimum. And the deflection of the spring is 15 mm, outside diameter is 30 mm, and ultimate tensile stress is 1393 megapascal, and shear stress as 606 megapascal. So in that question, they are asking um, they are asking the data, there is a deflection of the coil. Diameter of the wire is derived from the formula page number 7.10. We have some list of formula like Ks and C value. So one more thing is shear stress, that is also available in the page number 7.100. Use the formulas, you can find the wire diameter as 4.06. So we have to make it as a round value. Using the table, we got it as 4.25 mm. Then coming to the mean coil diameter, we are going to use the formula that is available in page number 7.100. In PSG data book, there is spring index equal to C equal to D by D. Use that and you find the mean diameter, and from that we can find the outside diameter of the spring. And coming to the number of active turns using the formula that is available in page number 7.100 in PSG data book, Y equal to 8 PC cube N divided by GD. So in this you have the only unknown is N. So substitute all the unknown and you will get the value as N equal to 14.57. And coming to the total number of coil, that is a formula that is available in page number 7.101 in PSG data book. So here I am considered squared and ground end. So for that the formula is NT equal to N plus 2. Substitute the unknown and you can get NT as 16.57. And coming to the remaining calculation as LS, in the same page you have LS formula Dn plus 2D. Substitute unknown and get the value as 70.4 mm. And coming to the next question, LF, there is LS plus Y. Substitute the unknown, it going to be 85.4. Then coming to the last question, pitch of the coil, that is LF minus LS divided by NT plus D. Substitute all the unknowns, it going to be 5.15. And coming to the helix angle and spring rate. So these formula you have to make up, that is alpha equal to tan inverse of pitch divided by pi d. So substitute all the value, it going to be alpha going to be 4.4. Then the spring rate is Q P max by Y. P max is, you have two things, maximum and minimum. Find the difference and divide the thing with deflection. You are going to get the spring rate of 23.3 Newton per millimeters. And coming to the next topic, belly spring. So normally we call it as cup and saucer type of spring. So it look like a cup like structure, saucer like structure. So we can have it in parallel or we can have it this in series for getting the better output. So these are all the formulas. Here we are going to find the load and the deflections. And coming to the spring material, normally we are going to choose chrome vanadium alloy steel, and allowable stress for this material is 1500 Newton per millimeter square, and Young's modulus 2 into 10 power 5, and Poisson ratio 0.3, and the thickness of the spring is 1 to 2 mm, disc, and diameter of the disc at the base is 28 to 300 mm, and H to T ratio is 0.4 for stiffness, and T by D naught ratio is 0.03 to 0.06, and cone angle is 4 to 7 degree. So for better value we are going to choose 6.5. And coming to one example from this belly, here they have given the thickness and outside diameter and the diameter ratio and inner diameter. So we are going to find the unknown, that is inner diameter, using the outside diameter and ratio, that going to be 50 mm. And free height of truncated cone is H value is given 4.5 mm, and maximum stress produced at the inner edge is given, sigma A is 560 Newton per millimeter squared. So we are going to find the unknown. So before that we have to find the constant like M, C1, C2. These formulas are available in page number 7.104. 104. So first one is maximum stress produced at the inner edge. So there is a formula sigma I. So substitute all the value and you can find the thing using a quadratic form of equation and solve it, and you can get it as a y equal to 0.703 mm. Then coming to the next load formula, substitute the unknown and also the y value, you can get it as 4.112 kilonewton. And coming to the another one, stress produced at the outer edge, that is sigma naught. This formula also available in page number 7.104 PSD data book. Substitute all the unknown, you can get it as 48.55 Newton per millimeter square. So that's all today. Thank you.